Hello, my name is Nicholas Ambrose, and today for my systems engineering project, I will be presenting search and rescue insect-like robots. All over the world, a variety of disasters occur all the time. Of these disasters, we will be focusing on building collapses. Buildings can collapse from many different causes, such as earthquakes, terrorist attacks, or being poorly designed. Two major issues that occur when the first responders arrive on the scene of a collapse are immediate dangers, such as unstable ground, secondary collapse, and explosions. The other issue is that victims that are trapped underneath the rubble are not easily accessible. So, the solution to these problems is to develop a search and rescue insect-like robot. This system will be able to assist search and rescue workers by scouting these dangerous environments. This robot can crawl through these small places underneath the rubble to help identify possible victims without risking human lives. The main importance of the system is that it saves lives. It improves the safety of the rescue workers by eliminating the need to physically crawl through rubble from collapses. This environment can be subject to further collapses that can injure the rescue workers. It also increases the amount of time that rescue workers have by helping increase their efficiency. This increased time ensures that victims are quickly discovered and treated. It is important to find victims that are in rubble very quickly because leaving them for a long time can cause further health issues. This robot will also help provide real-time video and sensor data to the first responders. This data can be used to make informed decisions, ultimately decreasing the risks. When working on this project, it is important to lay out a statement of work. So first, the project is being performed to provide the client with a robot that can be used to save lives in the event of a disaster. The correct hardware will be determined by using the client's requirements and their needs. Software will need to be developed for the project as well. The developer and the project team will be the ones performing the project activities, and the activities will be performed at the developer's facility. The client will pay the developer on a weekly basis to help cover the cost of labor and parts that are required for the system. The project will take approximately 35 days to complete. Both the client and the developer will meet the final week of the project to deliver the robot, install software, and to provide training to the client's team. The work breakdown structure breaks the project down into three main parts. These three parts include building the robot, developing the external control software, and developing general safety and safety training. First, building the robot consists of finding the parts and sensors required to meet the client's needs. Then, once the parts and sensors are identified, the control computer can be determined, and this computer is determined using the client's needs and the needs of the parts and sensors. The frame must then be designed based on the measurements of the parts and sensors. And then once the frame is designed, it can be created. The frame and the parts can be assembled. And then next, the robot software can be created and uploaded to the control computer. Then once the software is created and uploaded, as well as the parts and frame assembled, the robot can be tested. Next, the external robot control software consists of developing the software and interfacing it with the robot. Then, once the software is developed and interfaced, the software can be tested. Finally, the general and safety training for the robot need to be performed. The training is necessary to ensure that the client and their team can operate the robot in a safe manner. The developer's team will identify any safety concerns and develop a training guide. A training class can then be developed and tested. The following requirements hierarchical structure was developed for the system. It includes the insect-like robot system requirements. This explains how the robot will operate according to search and rescue operations. First, the robot walking requirement defines how the robot shall be able to walk on its own. This measures the effectiveness of the system. It is refined by a sub-requirement that defines the speed of the robot. This speed is set to approximately 10 meters a minute, and this measures the overall performance of the robot. The next requirement is the robot frame. The robot frame specifies how the frame will be built to hold the parts such as sensors and electronics. It is refined by two requirements, the frame material and the frame type. The frame material shall be built using 3D printed parts, while the frame type specifies that the robot shall have 6 legs. The next requirement is the robot components. This specifies what components will be used for the robot, such as the motors and the sensors that will operate the robot. So this can be broken down into two more sub-requirements, the ultrasonic sensor and the servo motors. So first, the ultrasonic sensor will be used to provide the robot with a range of at least 2 meters to help detect objects, while the servo motors will have a rating of about 25 kilograms per centimeter. This will help it to better navigate its environment. Both of these sub-requirements are key performance parameters for the system. The next requirement that we have is the safety system, which is required to prevent injuries to the stakeholders. Then we have the internal control software that is needed to control the software, to control the robot as it moves and operates. And finally, the external control software shall be used by the operator on an external computer to provide the robot with its mission. 7 types of engineers will each provide value to this project. These 7 types include the mechanical engineer, the electrical engineer, the computer engineer, the software engineer, the reliability engineer, the safety engineer, and the developer. First, the mechanical engineer will help to determine the strength required by the servo motors for each of the robot legs. They will also help to determine the frame of the robot. This frame will need to be structurally sound to hold all the parts. The electrical engineer will be responsible for developing the circuitry between the components. Different types of circuitry includes the printed circuit boards and the power supplies needed for the robot. The computer engineer will determine how the components operate and how they need to be programmed. For example, what protocols are needed, such as I2C or UART. Next, the software engineer will develop the internal and external software for the robot. They will also determine which programming language will be the best and the most efficient. The reliability engineer will perform calculations to ensure that the system does not fail, and it will also measure the maintenance required for the robot as well. The safety engineer will identify and document areas of safety concerns. And finally, the developer is the project engineer that manages the project team. They will use their technical and managerial skills to point the project team in the right direction, as well as ensuring that the team is productive with their time. Once all the components of the system are created, they will then need to be integrated together. There are many ways to perform integration of components for a system. For this project, I chose the subset implementation method. The subset implementation method groups all the components by their functionality. It then assembles them in these functional groups. The work breakdown structure can be used to determine and identify the functional groups of these components. Thus, this allows the assembly of the system to occur over time and happen incrementally throughout the project as these functional groups are being assembled. It also does not only apply to the assembly of the system, but to the testing. This allows the testing to focus on only components that grant and meet a specific functionality for the system. Risk management is an important part of any project. It ensures that risks do not overcome the project and cause it to be delayed or cause damage to the project. Therefore, the risk management plan for the project can be broken down into 3 sections: the risk identification, risk calculation, and finally risk recalculation. First, risk identification can be performed using a top-down approach, such as a fault tree analysis. One issue that the robot may have is that it does not move to the desired position. This can be broken down into 2 smaller issues and more detailed issues. One of these issues is that the robot does not move to the desired position because it does not move at all, or that it moves to the wrong position. So the robot not moving at all can be caused by 4 issues. These issues include the frame being broken, a sensor malfunctioning, a motor malfunctioning, or the internal control software malfunctioning. So when the robot moves to the wrong position, it is also caused by a few issues. These issues include a sensor malfunction or an external software malfunction. These bottom line issues can be used to determine the risks for the system. The risk identification method found the following risks, which include safety, software bugs, frame designed incorrectly, parts arriving damaged, and ordered parts arriving late. These risks can be described by a series of parameters such as severity, occurrence, and detection. Severity and occurrence are used to find the risk factor for the project, which is also used to estimate the risk assessment for the risk. Severity, occurrence, and detection are then used to solve for the risk priority number, which finds how important the risk is. So, looking at the failure modes, first one, safety, has a high severity and a medium occurrence. So this helps determine it as a high risk. Next, we have software bugs, which also has a high severity, but not as high as safety, but it also has a medium occurrence. This results in it also being a high risk. Next, we have the frame being designed incorrectly. It also has a high severity, much like the software bugs and the safety. However, it has a low chance of occurring. This sets it at a medium assessment risk. Next, we have the parts being delivered damaged. This has a high severity, but it has a low occurrence. So this sets the risk at a medium. And then finally, we have the ordered parts arriving late. This one is a medium severity and a low occurrence, so the risk is low. So using the severity, occurrence, and detection, we are able to rank the risks by the risk priority number as safety, software bugs, and then we have the frame designed incorrectly, parts arriving damaged, and the ordered parts arriving late. All of these risk parameters can be factored together to determine the overall project risk factor. This project was found to be a high risk project. The risks will need to be mitigated in order to help reduce the severity of the project risk. The table in the slide takes the risks from the previous slide and mitigates each and every one of them to lower the severity and the occurrence of them. So first, to mitigate the severity and the occurrence of safety, the safety risk can be reduced by increasing the integration of safety into the robot design. This includes reducing the speed of the robot and reducing the overall weight of the frame. The implementation of safety procedures can also help to reduce the risk for the operator. This in turn lowers the severity and the occurrence, dropping the risk into the medium range. Next, we have the software bug risk. This can be mitigated by using a third party to perform testing on the software. This will help to greatly reduce the occurrence of the risk and lower the risk from a high to medium. Next, we have the frame being designed incorrectly. This can be mitigated by performing simulations to verify its strength and perform inspections to also verify its strength. This will help to lower the severity and the occurrence, making it a low risk. The parts arriving damaged and the parts arriving late can both be mitigated by using multiple suppliers to purchase parts. When we have multiple suppliers, it lowers the risk of one supplier delivering the parts late, and it also reduces the risk of the parts being damaged from one supplier. So the multiple backup suppliers allow for redundancy when ordering the parts. Once all these risks have been mitigated, the new overall project risk can be calculated again. These mitigation strategies helped to lower the project risk from high to medium. Risk management is a continuous process, so these risks will be continuously monitored throughout the project and can be further mitigated to lower the overall project risk as the project develops. The stakeholders are also a major part of any project. They can either directly or indirectly impact a project. Each stakeholder has a combination of influence in the project, moral involvement, or importance to the project. These parameters can help to understand the relationship the stakeholder has and the impact they have on the project. First, the developer acts as the manager for the project. They ensure that it is completed as required and it completes on time. Next, we have the project team. The project team is the labor provider that will be performing the work on the project. Issues can occur if they do not follow the project plan. So periodical meetings can help to thoroughly lay out the plan to ensure that the project priorities and the timeline are clear. Next, we have the client, who is the customer for the project. They will help to define the requirements for the project. They can also have high expectations for the project and can change the requirements for the project accordingly. So it's best to implement a statement of work and satisfaction reviews. The statement of work thoroughly outlines what will be done for the project, while the satisfaction reviews will help to get feedback. Next, we have the first responders and the potential victims. These are both the users for the system. Since they are using the system, they will also have needs. It is important to meet with the users and perform surveys to understand how the system requirements can better meet their needs and how the system can operate to meet their needs. Finally, we have FEMA, which is the regulatory stakeholder of the project. Unclear guidelines can lead to issues throughout the project, so it is best to meet in person prior to kickoff of the project to fully lay out the guidelines that need to be followed when developing the project. A resource loading chart can be used to determine the usage of the resources for the project. The resource loading chart focuses on the usage of each of the project team members for the system. These members include the mechanical engineer, the electrical engineer, computer engineer, software engineer, safety engineer, reliability engineer, and the developer. Each line on the chart shows the percentage of work that each project team member is used per day. There are some instances where the team member is not required for the full day of work. Normally for a salaried individual, this will be a waste of potential and an unneeded cost. However, since each member on the project is a consultant that will be providing hourly work for the project, therefore they will not be getting paid for any unused time. In the future, the responsibilities of team members can be reviewed and identified to find ways to improve their performance and optimize the time. Other than the team members, the stakeholders also have responsibilities for the project and the project activities. First, the developer has managerial responsibilities for all of the project activities. They ensure that all the activities are being performed correctly and are meeting the project's needs. Next, the project team will facilitate all the activities, and they will be performing each of them as well. The client will be notified when all the project activities start and stop. They will also be providing approval for the testing of the frame, the testing of the robot, and the testing of the user training to ensure that it all meets their needs before moving on to the next task. Since the first responders are the users of the system, they will be notified when the key testing phases occur. This will ensure that they are up to date on their project activities and they understand that the project is running according to schedule. Next, FEMA specifies the guidelines of the system. They will be notified when the project starts in the identify parts and sensors activity, but they will also need to provide approval during the three main testing phases. To fully understand the project and to provide the most support during its development, it is critical to have an understanding of 4 areas of knowledge. These 4 areas of knowledge include robotics, Internet of Things, software development, and search and rescue operations. First, an understanding of robotics can help the team members to understand how robots operate and how they should be designed, both electrically and mechanically. Information can be found through the IEEE Robotics Automation Society. The Robotics Automation Society has a lot of information that can be used to help develop knowledge articles for this project. Next, we have Internet of Things, or IoT. IoT can help to understand how the robot will communicate with the external control software. IEEE has its own IoT community that can help with information concerning IoT. This information can then be used to also develop knowledge articles that can be referenced throughout the project. Software development consists of many practices and principles that can be integrated into the robot software. Much like IEEE, the Software Engineering Institute has information that can be referenced throughout the project. Finally, understanding search and rescue operations can help to understand how the robot must operate and the environments that the robot will be operating in. The American Society for Testing and Materials has many standards for search and rescue operations. This information can be referenced to provide a better understanding for the project. Next, we have the project communication plan. Communication is a major aspect of any project. Proper communication ensures that the needs for the project are met. There are 4 forms of communication that will be utilized for this project. They include meetings, phone calls, emails, and using a collaborative application. Meetings are set up by the developer and will involve the project team or another stakeholder. They will occur weekly to update the team on stakeholder decisions, to resolve project issues, and much more. Phone calls will mainly come from the developer and will be between the project team or another stakeholder. They will occur more often than meetings and will aid as quick discussions. They can be used to check on the status of the project, request work, or ask questions. Next, we have emails that will be coming from the developer to the project team or to another stakeholder. They will be much like phone calls, but are more formal and provide information or request in writing. It can be used for signing off documents and can also be used as a form of documentation itself. A collaborative application will allow the developer and the project team members to have quick and informal discussions internally. It will help the team to discuss, share information, share documents, and follow up on tasks. The project budget is used to estimate the total cost of the project. The cost for each day of the project is found using the resource loading chart. The hourly rate of each project team member is multiplied by the respective project team member's usage to calculate that project team member's cost per day. Then the sum of all the team members per day is calculated together. And then from that total sum, an additional 10% of that sum is added to it to cover the managerial overhead for that day of the project. This analysis is performed for each day of the project and graphed on the slide. So on day one, a certain amount is required for day one. Then as the project goes on, the cost per day is added to the total, showing the line that we see here. So the cost for the resources of the project is approximately $38,231.87. An additional $5,000 is added as a placeholder to cover the parts and materials required for the sensors, servos, and the frame of the robot. So the total cost of the project is approximately $43,231.87. Finally, the project schedule and key events can be seen in Figure 6. The critical path of the project activities is indicated by the red bars. These activities include identifying parts and sensors, identifying the control computer, ordering parts, assembling parts, testing the frame, testing the robot, and finally, the user training testing. A PERT analysis found that on average, the project will be completed within 23 days. This means that the project has a 50% probability that it will complete before or on the 23-day mark. However, as the amount of days added to the project increases, the higher the probability of completing the project on time. So even more time will be needed to the project in the event of unexpected risks to ensure that the project completes on time. So, to wrap up, the main importance of this project is to design a search and rescue insect-like robot to assist first responders in disaster scenarios. A team of 7 engineers will be performing this project. These 7 engineers include mechanical, electrical, computer, software, safety, reliability, and a developer. So far, we have found a total of 5 risks that will be present within the project. We have then mitigated these risks to reduce the project from an overall high-risk project to a medium-risk project. The risks will be continuously monitored throughout the project, and they will be mitigated as it is seen fit to further lower the risk of the project. Next, the resource loading and budgeting found that the project will approximately cost $43,231.87. This number includes the cost of project resources with a 10% managerial reserve. An additional budget has been set aside for the cost of parts and materials. A PERT analysis found that there is a 50% probability that the project will be completed in 23 days or less. So any additional time added to the project will help increase the probability of the project completing on time. Additional time may also be required to mitigate unknown risks that are found. All in all, this systems engineering plan will be used to develop a system that will help save lives in the future. That is all I have for today. If you have any questions, please feel free to reach out and contact me. I look forward to hearing your comments. I hope you have a great day.